Hey guys, Andy Robertson here with Greenbelt Academy, and I am so excited for today's video. I've always said that taking practice exams is one of the best ways to prepare for the Greenbelt exam. So in today's video, I want to share with you 10 questions that you might see on the Greenbelt exam, along with how to actually go about solving the problems, and a free resource to help you look up the right equation on exam day. All right, let's head over to the computer and get started.
All right, let's take a look at today's agenda. So if you are preparing for the Greenbelt exam, you should know that the Greenbelt exam has 100 total questions spread across 6 major pillars: overview, define, measure, analyze, and prove, control. We basically follow the Domatic model with this overview pillar here first to capture some of the extra topics. Now, on the Greenbelt exam, there are really 2 types of questions. There are knowledge questions, like what type of tool is being described, or what concept or tool would be best used in this situation. And there's also calculation type questions. Now, for the purposes of today's video, I'm focusing more on the calculations because this is where most people get tripped up in the Greenbelt exam, is when they have to use some of the statistical tools and calculations and methods that are required in the body of knowledge. Now, all of the 10 questions that I'm going to show you today come from my course, the Greenbelt Masterclass, but I also have other free practice exams that you can use to help prepare for the Greenbelt exam. I will add links in the description below for you to get those for free. The other thing I want to show you today is my exam day cheat sheet. So again, this is a free tool that I give everyone who signs up for my free course, the top 10 topics on the Greenbelt exam, where essentially I give you a resource that has every single equation on the Greenbelt exam. It's everything you'll need on exam day. It'll help you look up the right equations and save time. So as we go through the 10 questions today, I'm going to show you how you can use this cheat sheet to quickly look up the right equation for every question that we run into, okay? Okay, so real quickly, before we jump into those 10 questions, I want to give you an overview of what we're going to cover. These are the 10 questions. Number 1 is all about OEE, or overall equipment effectiveness. Number 2 is statistical process control. The third question is going to be a takt time calculation. Number 4 is all about process capability. 5 is hypothesis testing. 6 is Poisson probability. So this is how to calculate the probability of discrete data or discrete events. Number 7 is calculating the number of treatments in a DOE. If you're going to run a DOE, you have to be able to calculate the number of treatments that are going to be required for the design that you selected. Number 8 are major process metrics like Rolled-Throughput Yield, so we'll do a calculation there. Number 9, and I love this one, is the probability of a sample mean value. The central limit theorem, the distribution of sample means, is a really important concept in statistics and in Six Sigma, so it's really important that you understand this question. And then lastly is confidence intervals for the population proportion. I absolutely love this question, and let's go ahead and jump in and get started with the very first question. So the way this whole thing is going to work is at the top of the slide, I'm going to tell you the topic. On the Greenbelt exam, all the questions are random, so they're not going to tell you what topic it is that you're being asked about. You have to infer all of that from the information given. So what I'm going to do is I'm going to show you the problem statement, and then I'm going to help clue you in. I'm going to show you clues within the problem statement to help you understand how to select the right problem statement. So here in this problem, what is the OEE value for a process that produces 668 good parts out of a 700 total built in a scheduled plan time of 16 hours, where we had 2.5 hours of unscheduled downtime and a performance of 91.6%. Now, right off the top, the very first keyword that you should focus in on is this idea of OEE. If you ever see a question that asks you specifically for the OEE, you got to look up the OEE calculations. So on page 11 of that exam day cheat sheet, which you can find linked in the description below, I've got all of the equations that you might need on the Greenbelt exam related to OEE. And so you'll notice here we're going to use most of these equations here, and then finally we're going to wrap up with the OEE calculation. Now, the other thing I like to help people do is as you read a problem statement, it's important to again, focus in on keywords. So what I've done is I've taken that problem statement and I've adjusted it to kind of highlight keywords in specific colors to help you relate that back to the equation that you need to use. So at the bottom here, remember, OEE, or overall equipment effectiveness, is a combination of 3 factors: performance, times availability, times yield. So to solve this problem, we're going to have to calculate availability and yield. And of course, we're given performance in the problem statement of 91.6%. Okay, so yield, right? If we go back to that equation cheat sheet, you'll find this equation right there at the top. Yield is equal to the good parts produced divided by the total parts produced. So again, if you read that problem statement, we had 668 good parts out of 700 total, meaning that our yield is 95.4%. The other thing we have to calculate is availability. So the availability of your equipment is calculated as the actual runtime divided by the planned runtime. Now, in the problem statement, we're told that we have a scheduled planned time of 16 hours. That's the denominator. The actual runtime was the planned time minus the downtime. So we had 2.5 hours of downtime, meaning that we actually ran for 13.5 hours. 13.5 divided by 16 means that our equipment was available 84.4% of the time. Now that we have yield and availability and performance, we can calculate OEE 91.6 performance times availability times yield means that the overall equipment effectiveness for this particular shift was 73.7%. Make sense? Okay, the next question, and these are really common on the Greenbelt exam, is all about statistical process control. And the types of questions that you'll see are calculations specific to control limits. So let's read this problem statement and figure out the right equation that we need to use. You manufacture a widget, and you use an X bar and S chart to control the critical feature of your product. Your normal process has the following attributes. X double bar is 16.75, S bar is 1.35, and your sample size, your subgroup sample size is 15. Identify the upper control limits for the S chart. Now again, if we go back to that exam day cheat sheet, what you're going to find is that for the X bar and S chart, I not only give you all of the equations for the grand mean and the control limits for X bar and the control limits for S bar, I also give you all of the constants that you'll need to actually perform this calculation. You'll notice here that for the upper control limit for the S chart, we need to know the B4 factor. Okay, so I'm going to show you how to do that here in just a second. Here's that equation, upper control limit. It's B4 times S bar. If we go to this little table that's included in that cheat sheet, the way you look up the B4 factor is by using the subgroup sample size. So here in the problem statement, we had 15 samples per subgroup, right? That's here, that's 15, that's this first column. We come across to the B4 factor, and we find that for our subgroup sample size, it's 1.572. And now all we have to do is plug in the calculation. 1.572 times S bar, 1.35, gives us the upper control limit for the S chart to be 2.12. Okay, let's keep going. Okay, question number 3 is all about takt time. So let's read the problem statement. Your takt time is 36 seconds. You run 2 shifts per week, each at 40 hours per week. What is your monthly demand? Assume 1 month to be 4 weeks. I love this question because it's takt time in reverse. You're given the takt time, and what you're being asked to solve for is the customer demand. So again, when you see keywords like takt time, you can go to your exam day cheat sheet and you can find the equation associated with takt time. Takt time is equal to your available production time divided by customer demand. So let's go ahead and complete this calculation. We're given takt time. We want to solve for the customer demand, and we're also very subtly given the available production time in the problem statement. So let's now calculate the available production time. 4 weeks per month, we're told to assume that, times 2 shifts per week, times 40 hours per week, times 3,600 seconds per hour gives us an available production time of 1,152,000 seconds per month. And essentially all we have to do now is rearrange this equation to solve for the monthly demand. We move the monthly demand over here, we move takt time underneath to the denominator, and what we find is that our monthly demand is 32,000 units. To meet this customer demand, we have to be producing a part every 36 seconds. Make sense? Okay, let's move on to the fourth question here, which is all about process capability. I love this question. You know, it's really important, I think, for you to understand that process capability and statistical process control go hand in hand. We use control charts, not just to make sure that our process is in control, but also to collect the data that we need to perform the process capability calculation. So oftentimes these process capability calculations come to us almost in the form of a control chart type question. So let me give you an example. You manufacture a product to a specification of 10.6 inches plus or minus 0.2 inches. You control your process with an X bar and S chart with a sample size of 15, and your X bar value is equal to 10.55, and your S bar value is equal to 0.06. What is the capability or the CPK value of your process? Okay, so obviously that last sentence there cues you in on what type of question it is you need to solve. And when you go to your exam day cheat sheet, here's all of the relevant equations for process capability. You can see it here in yellow. Here's the calculation we're going to use. I've also highlighted this really important phrase in purple that I think is important for you to understand. the process capability calculation that you perform on the Greenbelt exam or in real life should use data that comes to us from a control chart. And when we use a control chart, what we have to do is we have to take S bar or R bar or our moving range value, and we have to translate that into an estimate of standard deviation. And that's why this particular calculation is so complicated. Now, to do that calculation, again, we're going to have to take S bar and convert it into a measure of standard deviation. And again, that's going to require you to use this little table here for the X bar and S chart because it includes this C4 variance factor that we're going to use in this particular equation. So let me show you how to work this problem. Again, what I've done is I've taken the problem statement and highlighted the key parts to help you understand how all this information from the problem statement is going to be used in the actual calculation. So in this red color, I've highlighted the upper specification limit and the lower specification limit. That's an important part of the calculation. It relates back to customer specifications or customer requirements, and that also comes to us from the tolerance or the specification for our product. The other thing we have to know is the average value for our process. Again, this comes to us from a control chart in the form of X bar. You know, if you've got a control chart and you've got an X double bar value, that's the average value of your process. And then what we also have to do is we have to take our S bar value, which is the average sample standard deviation from our control chart, and convert it into an estimate of the population standard deviation. So here's that equation. We can estimate our population standard deviation by taking S bar and dividing by the C4 factor. Okay. Now remember that C4 factor comes to us from this X bar and S chart where our subgroup sample size is 15. We come all the way across. Our variance factor, the C4 factor, is 0.9823. You can see that here in the denominator. And essentially we can translate our S bar value into standard deviation and complete the calculation. 10.8 minus 10.55 divided by 3 sigma. That's the upper CPK value. This is the lower CPK value. When we work the math, essentially what we find is that the minimum value between these two separate calculations is 0.818, which is our CPK value for this given situation. All right, makes sense? Let's keep going. Hypothesis testing. Here we go. This is a big question. This is a big topic on the Greenbelt exam. Let me give you kind of a sample problem. You've performed a hypothesis test for the population mean value, which you believe to be 8.75 inches. Maybe that's the historical value, or maybe that's what it's been historically. And you sample 40 parts, and what you find is that the mean value of that sample is 8.60 inches. The population standard deviation is known to be 0.90 inches. What is the test statistic for this hypothesis test? Now, again, this question really telegraphs kind of the calculation that you need to use. But if you're asked a hypothesis test question, the exam day cheat sheet has all of the hypothesis testing information or statistics right here on page 4. And what you'll find is that for the sample mean value, this is the calculation that we're going to make. Because we have more than 40 parts, we can use the z-score and the z-transformation to essentially calculate our z-statistic. By the way, on the right-hand side of this exam day cheat sheet, I've got this use when column. So you use this equation when the population variance is known and the sample size is greater than 30. Both of those conditions are met in this problem statement. So we now need to use this particular equation to calculate the test statistic for this hypothesis test. Now, I love doing this. I love kind of color coding and helping you translate the problem statement into the parameters that you need to plug into the equation. So for example, the sample mean value, X bar, is equal to 8.60. The population mean is equal to 8.75. The population standard deviation is 0.90. And the sample size is equal to 40. And if we take all that information from the problem statement and we plug it into this particular calculation, we can calculate the test statistic for this hypothesis test to be negative 1.05, and that is the answer for this problem. All right, let's keep going. Probability. I love probability calculations, and one thing that often comes up on the Greenbelt exam is not just probability for the normal distribution, but also probability when using discrete data or attribute data or counted data. So I wanted to give you an example of how to calculate probability when dealing with discrete data. Okay, your production lot has an average defect rate of 9 defects per lot. Okay, that's an important piece of information. what is the probability that a lot is produced and exactly 3 defects are observed? So obviously there's a handful of keywords here, probability being one of them, right? If you see that word probability, you know you have to calculate the probability of some value. Now the next keyword here is exactly 3 defects. That is the outcome that we're concerned with. And when you're counting up defects, you should immediately associate that with attribute data. Now, when you're using attribute data, the other question that you kind of have to answer in your mind is, should I use the binomial distribution or should I use the Poisson distribution? And so when you read this problem statement, the other piece of information or the other parameter that you're given is that your production lot has an average defect rate of 9 defects per lot. Okay, so when you're looking at your exam day cheat sheet, the parameter that you were just given is this value. It's lambda. It's the mean number of occurrences. It's the average number of defects per lot. And so when you see lambda or when you see that average defect number, you know that you have to use the Poisson probability calculation to calculate probability. And here's that Poisson probability calculation. Let me show you how to work this calculation. So I've highlighted the parameter and the value that we care about. Lambda, our average defect rate, is equal to 9, and the probability that we're solving for is exactly 3 defects. What is the probability of getting exactly 3 defects when we average 9 defects per lot? So I've plugged in lambda as 9, and I've plugged in x is equal to 3. Now what I want to do is I want to show you how to work this particular problem, and it really all starts here in the denominator. See this word here, this denominator here, 3 factorial? What does that mean? So a factorial, like 3 factorial or even 10 factorial, is essentially that number, 10 times 9 times 8 times 7 times 6 times 5 times 3 times 2 times 1, all the way down to 1. 8 factorial is 8 times 7 times 6 times 5, all the way down to 1. And of course, 3 factorial is 3 times 2 times 1. Anytime you see this exclamation mark, that means it's a factorial, and this is how you work the math. So we can take this 3 factorial and translate it into a value of 6. The other thing I like to do is on my calculator, I like to work these terms independently. 9 cubed, I take E, which is Euler's number. That's a mathematical constant, 2.718. I raise it to the power of -9. I multiply it times 9 cubed and divide by 6, and what I get is 0.015, which is also equal to 1.5%. I like to show people how to find Euler's number on their calculator. I use this Texas Instruments TI-30X, and essentially to do this equation, I have to hit the second button, I find the natural log, I hit that button, and that brings up this equation, E raised to the power. I typed in -2.828 just as an example. You could type in -9, and of course you'd get the right answer for this solution. But that is how you essentially plug this into your calculator. Okay, let's keep moving here and talk about design of experiments. When you are designing an experiment, again, it's important to be able to calculate the number of treatments associated with whatever design you've chosen. So, how many treatments would be required for a DOE that has 4 factors where you've chosen a quarter factorial design, okay? So again, some of the keywords here in the statement are treatments and quarter factorial design. Those are the 2 keywords that you need to know to look up the right equation. So again, if we go to page 11 here, the exam day cheat sheet, all of the equations for design of experiments are included here. Full factorial designs, half factorial designs, and quarter factorial designs. You can see all of the equations here. I also give you this little table here that you could just look. In fact, the answer is included on this table. Don't look at the table. I want to show you how to work the equation first, and then show you how you can use the table to just quickly identify the right answer. So let's take our equation, quarter factorial design, and let's actually work the math. So the number of treatments for a quarter factorial design is equal to, we've got 4 in the denominator, and then in the numerator here, we take our levels and we raise them to the factors. Now, if you look at this problem statement, you're not told how many levels are associated with your DOE. For the Greenbelt exam or even for the CQ exam, it's assumed that you're doing a 2-level experiment. 3-level experiments and 4-level experiments are outside the body of knowledge. So if you are doing a DOE problem on the Greenbelt exam, if you're not explicitly given the number of levels, assume it is a 2-level experiment. Now, what we are given By the way, we can simplify this equation as L to the F, levels to the factors, divided by 4. It's a quarter factorial design. We have to divide by 4th because we're going to do 1/4 of the total number of treatments. So we can take levels to the factor. We can convert that into 2. We're going to do a 2-level experiment, 2 raised to the F, divided by 2 squared, right? 2 squared is equal to 4. We just changed that into an exponent. And of course, we can simplify this equation. Anytime you have a fraction with exponents, you can actually, instead of doing a fraction, you can say f minus 2. So I've simplified this equation. We have 4 factors. So 4 minus 2 is equal to 2. 2 squared is equal to 4. So the number of treatments for this design is equal to 4. There's much easier math. Instead of doing all this fractional stuff with f minus 2 and all that, you can just plug in the information you have. Levels to the factor is 2 to the 4th. That's equal to 16. 16 divided by 4 is equal to 4. You can also just simply use the table. So back here on the exam day cheat sheet, we have this table here where in the left-hand column, we've got the number of factors. So in this problem statement, we're told we have 4 factors in our design. If you were going to do a full factorial experiment, you'd do 16 treatments. Half factorial design would be 8 treatments. And for a quarter factorial design, you would do 4 treatment groups. And that is the answer. You can either work the equation or you can just use the table that I've given you in the cheat sheet. It's probably easiest just to use the table. That way you don't accidentally make a mistake with the math. Okay, let's keep going. Next problem is all about rolled throughput yield. When you're characterizing your process and you're trying to describe the performance or the quality of your process, rolled throughput yield is one of the Lean Six Sigma metrics that you can use. So I want to make sure you understand how to calculate this particular metric. And so this is, by the way, this is a question that comes up on the Greenbelt exam. You have an operation with multiple steps, 1, 2, and 3. Using the following data, calculate the rolled throughput yield for this process. Now, again, if you use the exam day cheat sheet, you can go to page 15 and you can find all of the process metrics, defects per unit, defects per million opportunities, along with rolled throughput yield, which is the one we're going to use now to solve this particular problem. So rolled throughput yield is equal to the yield of step 1 times the yield of step 2 times the yield of step 3. Now we have to calculate the yield or the yield loss associated with each step in our process. So I've added little columns here to calculate the yield loss and the yield for each of our steps. So for step 1, we had 19 defects out of 400 total produced, meaning that our yield loss was 4.75%. I can do that same math for steps 2 and 3. Now, to actually work the calculation or the equation, we have to convert yield loss into yield. So in step 1, we lost 4.75%. We yielded 95.25% of good parts. Okay, this is good parts. These are bad parts. And of course, the final rolled throughput yield calculation is simply just the individual yields from each of these individual steps. 95.25 times 91.45 times 89.68 gives us a rolled throughput yield of 78.1%. By the way, you can jump straight to the yield calculation and totally skip this whole yield loss thing. That's probably an easier way to do it, but I wanted to show you both methods. Okay, let's keep going here and talk about the probability of a sample mean. I absolutely love this type of question. So, a manufacturing operation produces a part that follows the normal distribution. Historically, it has a mean weight of 12 ounces and a standard deviation of 1 ounce. Estimate the probability of taking 9 samples and finding a sample mean value greater than 12.4 ounces. Okay, so again, if you're using continuous data and you're looking to calculate probability and you've taken samples, right? You've taken a sample, the right equation to calculate probability uses or requires that you use the distribution of sample means. Okay, this is on page 2 of the exam day cheat sheet. When you take a sample and you want to find the probability of some sample mean value, you have to use the distribution of sample means. So we are going to convert this mean value into a z-score and then ultimately look up the probability associated with that z-score. So here's that equation. This is how we're going to calculate the probability of a sample mean value. And of course, we're given some information in the problem statement. The historical mean value, 12 ounces, and the population standard deviation of 1 ounce. We're also given the sample size of 9 and the sample mean value of 12.4 ounces. So all we have to do now is fill in this information, calculate the z-score, and then look up the probability of this particular value. When you plug all this into your calculator, you can transform this sample mean value of 12.4 ounces into a z-score of 1.2. Now you're not actually done with the problem. Now what you have to do is pull up your normal probability table, find this z-score, and look up the probability associated with that particular value. Now in this table, it's 38.5%. Now that's not the final answer. Let me show you what the final answer is. And I want to help you visualize this. All of the probabilities shown in this normal probability table, right? If you look at all these values, what that represents is the area under the curve between that z-score and the mean value. So here's the mean value, here's the z-score of interest 1.2, and this value in the table of 38.5% is actually the area under this part of the curve. What we're trying to solve for is the probability of taking 9 samples and finding a mean value greater than 12.4 ounces. So what we really care about is the area under the curve greater than that particular z-score. And the way we calculate that is we essentially say 50% minus 38.5. Remember, the normal distribution is symmetric around the mean. Half of the population falls on the left side, half of the population falls on the right. And so if we know 38.5, we can solve for 11.5 by just saying 50% minus 38.5% is 11.5%. There is a 11% probability of taking 9 samples and finding a sample mean value greater than 12.4 ounces. Make sense? Okay, last problem. Here we go. Confidence intervals for the population proportion. Okay. Now, I like this question because it directly relates to you as a greenbelt. Oftentimes, one of the most important metrics we care about as, continuous improvement professionals is things like yield, right? The yield rate or the defect rate, something like that. And so this is a statistical method that you can use to actually estimate or create a confidence interval around your population proportion or your population defect rate. So let me show you how to do that. You have sampled 50 units from the latest production lot and found that 3 of those 50 items are non-conforming. Find or create the 95% confidence interval for the true population proportion of defective products, okay? So again, I've highlighted the statement here that you should really clue in on, and it's 95% confidence interval for the true population proportion. So if you go to page 4 of the exam day guide, you're going to find all of the equations for the confidence intervals. Now, you could create a confidence interval for the population mean or the variance or the standard deviation, or finally here at the bottom, you can create confidence intervals for the population proportion. So here's the equation that we're going to have to use, and let me show you how to work that equation. Okay, so if we look at the problem statement, we're given some information, okay? We're told that we sampled 50 units, and we found that 3 of them are non-conforming. So the first parameter that we have to calculate is this p-value, which is the sample proportion. In the sample we took, what is the defect rate or what is the proportion within that sample? So we take 3 and we divide by 60, and what we find is that in that sample, we had a 6% defect rate or a 6% proportion. Now, the other thing that we have to include in this equation is a z-score, okay? Now, in the problem statement, we want to find the 95% confidence interval, and lucky for us, the population proportion follows the normal distribution. So when you want to find the 95% confidence interval, you can quickly use the z-score. There's some really common z-scores that come up all the time on the Greenbelt exam. This is one. So the z-score associated with a 95% confidence interval will always be 1.96. That's also included in the exam day cheat sheet, and I've included it here for you as well. So now what we can do, now that we have the sample proportion and the z-score, we can essentially work the math and fill out this particular equation, which gives us a confidence interval of 0.06 plus or minus all of these numbers. We can continue to kind of work this math. And what we find, by the way, I want to point out something really interesting. So we're going to do 6% plus or minus 6.6%. On the lower side, when you take 6% minus 0.066, you get a negative number. It is impossible to have a negative defect rate, so we round up to 0 as part of that interval estimate. So the right answer for the 95% confidence interval is 0 all the way up to 12.6%, and that is absolutely it. By the way, if you want to get that exam day cheat sheet that I've been showing you throughout this, go to greenbeltacademy.com/cheat sheet. Again, you're going to get all the equations that you need to be successful on the Greenbelt exam. The other thing I love to give people is a free course that covers the top 10 most important topics on the Greenbelt exam. Again, you can get that totally for free, greenbeltacademy.com/free course. By the way, if you really like this video, do me a favor. Hit that like button. That way other people just like you can find the same content and benefit and grow and pass the Greenbelt exam. And if you really want to stay in this journey and you're really serious about becoming a Greenbelt, hit that subscribe button. That way as I publish new content, you get notified and you can stay on this journey and continue growing and continue learning. All right, that's it for me. I hope you enjoyed it, and I will see you in the next video. Thanks so much. Bye.